Again, welcome to quantum computing. We have been learning some really nice algorithms, and it's time to expand our algorithms to come to natural problems. So let's see what we have learned and try to understand what we can solve on a quantum computer. The last two algorithms we have seen are Bernstein-Masrani and Simon's algorithm, correct? We have seen, so what was Bernstein-Masrani? We are given a function from 0,1 to the power k to 0,1, correct? Right? This is a function which takes a string of length k as input and answers 0, 1. Were we supposed to compute this function? No. We are given this function as a black box. So we have a black box. We can give it a string and it will tell us what is the function value. Correct? Also, we are given that our function is of this special form. Okay, and our goal is to find A using minimum number of queries to the oracle. Agreed? This is the problem we wanted to solve for Bernstein-Masrani. And I want to emphasize that Simon is not very different. Okay, in the Simon case, we are given again a function from 0,1 to the power k to 0,1. Same thing. It's just that the structure has changed. Instead of saying that my function is a times x mod 2, I am saying that there is a hidden string s, or there is a period inside the function. The period is the string s such that f of x is equal to f of x XOR s. So anytime I take two strings which are s apart, which have a distance s or which are related by x and x XOR s, they are going to have the same color. And again, we wanted to find this particular property for Simon's algorithm, right? And then if you look at the solution, if you look at the circuit for these, the circuits were basically, what was your solution? You create equal superposition over all, how many elements? 2 to the power k elements. You create an equal superposition, apply f. What does f do? Oracle does, it applies function f, correct? Either as a phase or as in the next register or something. But we calculate the function value and then applying the header word gives us the solution, right? Wait, this is a solution for Bernstein-Masrani or this is the solution for Simon? How many think this is a solution for Bernstein-Masrani? How many think this is a solution for Simon? Yes, this is a solution for both. This is what I want to emphasize. That even though the structure is slightly different, the only difference was, which is not a big difference, in Bernstein-Masrani, the oracle was the phase oracle. Correct? And in Simon's, this oracle was the regular oracle, which computes the function value in the register. Yes. Suyesh, you have a question?
If Bernstein-Masrani is like a special case of Simon's?
No, it is not. And I will tell you this. Very good point. So this is what we want to figure out. What I want to tell you is that they have almost the same looking solution. They have almost the same looking pattern. Is there a relation between these algorithms in these problems? This is what I want to understand. What do you think? There should be something, right? It seems so similar. The functions are defined on the same domain. There is just a slight difference in the function structure, but still both we can find by applying similar strategy. And by the way, I can tell you that even if you apply the regular oracle in Bernstein-Masrani with slightly more, still constant number of queries, you can still solve Bernstein-Masrani. So there is nothing special about applying the phase oracle. And you know that phase oracle and other oracles are actually same. It's just what is easy to present, what comes intuitively. So in that sense, these solutions are very, very similar. So what is the relation between them? Or other way to say it is, we will see why are we applying this header method? What is the significance of this header method? By the way, how many people were able to see the video I shared? Okay, so this is my mistake. I should have shared it earlier. So I apologize for that. So what we will do is we will talk about this few things as the basic, but I still heavily recommend you to read that, watch that video. Okay, it will be helpful. So my apologies for sharing it too late. Right. So even if it doesn't emerge directly, but you see that these seems to be related, right? These two algorithms, Simon and Bernstein-Masrani, seem to be related. Yes, no? You don't want to find how they are related? Yes, no? Yes, you are sitting in the class, you have no other choice. You have to say yes. Right? So, what is the relation between them? This emerges from, if you look at this group, z to the power k. Right? What is this group? This is a group where we have all the elements are strings of length k. This is basically this set where we are allowed to add two elements. And how do we add? We add them entry wise, take modulo 2. Right? So this is the group z to the power k. Correct? So our function I can write as z to the power k. Okay? And let's take an example. And this we have done before, right? So in the case of Bernstein-Masrani, I am dividing my cube. So this is when k equal to 3. Right? When k equal to 3, in case of Bernstein-Masrani, I am dividing my cube into how many parts? 2. My function value is either 0 or 1. So I am dividing into 2 parts. Depending on a, whenever a dot x is 0, again everything is modulo 2. Then I say color blue. If a dot x is 1, color red. Right? So I don't have a colored chalks, but okay. Right? I divide my cube into 2 parts. One is colored blue, one is colored red. On the other hand, for Simon, I am saying that every 2 get the same color. Correct? So this and let's say this get the same color. This and this get the same color. This and this get the same color. And this get the same color. Correct? So if you now look at all the elements which have the same color as 0. So this is 0, 0, 0. This is 0, 0, 0. Correct? So if you look at all possible A's, you look at the color set which is where 0, 0, 0 is contained. That is actually in some sense the biggest subgroup of z to the power k. Okay, and this is something which I emphasized in the group and subgroup, that you are given a group, this is z to the power k, you take a subgroup, the cosets of the subgroup actually divide the group or partition the group. And if you are still not clear about the subgroup and the cosets, in Bernstein-Masrani, the subgroup is the biggest, and so these are the different color classes, right? And what I'm saying is they are related by a group structure. In case of Bernstein-Masrani, there are going to be 2 parts. The 0, 0 part is in some sense the biggest subgroup possible inside the group. In case of Simon, there are going to be lot of groups, a lot of cosets, right? How many cosets? To the power k minus 1. Every coset is corresponding to a color class. And this is the subgroup which corresponds to where, what is the color of 0, 0, 0, right? So if I take these two elements, they are going to form a subgroup. And these are the smallest subgroups of Z2 to the power k. So both problems are solving this structure where you have some subgroup and all the cosets are colored the same. Again, you can read about the cosets, but for now, assume that there is, from the subgroups, there is some structure. There is this nice partition. Every time you have a subgroup, it gives you a nice partition. For Bernstein-Vazirani, these partitions are big. The number of partitions are small. Each of the partition has the same color. In Simon, the partition is very, very small. It has just two elements. It's the smallest partition possible. But the number of partitions are pretty big. Actually, just give me a second, Suyash. Actually, you can have any subgroup in between. Not just the biggest or smallest. If you give the cosets the same color, the same algorithm actually works and finds out the subgroup for you. This is the essential property we are going to use in lot of algorithms, even for Shor's algorithm. And the reason why we can find this subgroup is because this is a Fourier transform over Z to the power k. Okay, the take home message at this point is, even if you don't know about cosets and Fourier analysis, what problems we have solved and even Deutsch-Jotza can be put in this framework where all the cosets, all the partitions are colored the same for a subgroup. A subgroup leads to a partition. If you have a function which colors the partition the same, every partition of the same color, then I can figure out what the subgroup is by using Fourier transform over that group. What is Fourier transform? Watch the video. What is this partition structure? You can figure out using, again, the lecture video. Okay, but what we will remember is that every subgroup leads to a partition. Okay, so a subgroup leads to a partition. You give me an information about partition. How are you giving me information about the partition? You are giving me a function which is constant on each part. Then using Fourier transform, I can tell you which subgroup you started with. Okay, so this is what we did in Bernstein-Vazirani, this is what we did in Simon, and this is what we are going to do for a long time. So almost all the quantum algorithms known can be divided into two parts. One is this Fourier transform based algorithms, other are the amplitude amplification based. That's why this idea I am trying to emphasize. This idea is very, very important. This is used in almost half of the algorithms, known quantum algorithms. Fourier transform is good in finding these periods or these partitions. What are these partitions? What exactly is Fourier transform? That you will have to read. Okay, if you already don't know that. So sorry, you had a question I asked.
Shouldn't there only be two partitions in the Bernstein-Vazirani?
Oh, this one? Yeah, I was drawing a general graph and then, so you are completely right. If I want to write it for Bernstein-Vazirani, then this is the picture. So now this is BV and this is Simon. Thank you. Yes, I was trying a general picture and then I said, let me draw two pictures. That's why. But yeah, Bernstein-Masrani is going to have just two parts. Simon is going to have 2 to the power k minus 1 part. Okay, and you can do everything in between. Okay, so again, to give you what Fourier transform does is actually concentrates the amplitude on nice characters which reveal the subgroup. But again, that's something we will understand later. For now, whatever algorithms we have seen, they have a nice structure. We can capture that structure by saying that for this particular group, we can apply Fourier transform. And hence, we can reveal these partitions. Okay. So now, I have told you this story that we have this nice group z2 to the power k. For this group, since we have the Fourier transform, we can reveal this partition, we can reveal the subgroup given the partition as a function. Now, if you are a researcher, what will be your thought? Very good question, right? First thing is, whatever problems we have solved, right, till now, they seem slightly artificial. Okay, very artificial. We just wanted to show that quantum has advantage over classical. But so now the question is, are there subgroups of z2 to the power k where the problem becomes natural or fun? Probably no. Then what do we do? What will you do next? Good. That's a very good thing to think. Why restrict ourselves to? Are there other groups where we can do Fourier transform? Like the Fourier transform, Hadamard has given us a lot of information about z2 to the power k. We know so many groups. Is it possible to do Fourier transform over other groups? That might be useful in the natural world. And that's what we are going to see. So, Fourier transform is something which has helped us over one group. So, why not see other groups and find out if Fourier transform helps over those groups? Obvious, no? So, let's see. What are the other simple groups? Z2, just two elements, 0, 1, right? That was a simple group. We know the Fourier transform. What is the Fourier transform over Z2? Hadamard. Okay. Now you can think of Z2 to the power k, or the other way to extend it would be Z3 or Z4 or Z to the power k. It is very, very important to notice that this group and this group are very different. Okay, the elements, the number of elements are going to be 2 to the power k. This is when elements are binary strings. These are numbers 0, 1 to the power k minus 1. More importantly, when you add here, how do you add? You add coordinate wise. Correct? Modulo 2. Here you add modulo 2 to the power k. Okay? So, even though they might look similar, they may have same number of elements, these two groups are very, very different. Okay? Now, for the next thing would be to define Fourier transform over this. Yes?
The input is, length of string of input is still 1, right? In Z3, Z2, Z3.
In this?
Yeah. In these, the inputs, like the elements are, or strings of length 1, right?
See, the elements are, these groups are some abstract object, right? Whatever abstract object you take, when you represent it on a computer, even an image or a video is basically 0, 1 string. So even when we will represent these elements, we will represent them as qubits or bits on the quantum computer, because that's what you do. The point is here, for example, if I add these two, what will I get? 0, 1, 0. I am adding coordinate wise modulo 2, right? So I am getting 0, 1, 0. On the other hand, if I am adding here, this is 1. This is, oh, yeah. So the addition is going to be 1, 0, 0.
So we are essentially representing some, instead of 0, 1, we are representing 0, 1, 2, 3 as 0, 0, 0, 1.
Because our computer allows us only to represent them as bits. So that is irrespective of what the group structure is here. This is math. Images, video, whatever you have to put on the computer, you will write it as bits. So even these elements, when you write them, you will write them as bits. Even for Z3, you will have one kind of, you will write as 0, 0, 0, 1, 1, 0, 1, 1 will be empty. You will never use 1, 1 in your computer. But that's what you will do, because your entire hardware is based on qubits. And this is not special. You can make probably a computer with qubits. But then you really don't want, when you want to solve a problem on Z3, you don't want to make a qubit computer. When you want to solve a problem on Z4, you don't want to make a, whatever is the 4-bit computer or something, right? So that's why the representation is independent of the mathematical reality. Sense? Okay, good. So now we want to do Fourier. So this is very good. So now you will see how these two are different, right? These are different groups. Correct? So now we want to do Fourier transform over Z2 to the power k. I will show you how to do Fourier transform over Z2 to the power k, why it is great, okay, and so what is Fourier transform, what is the matrix, I will write, but to verify that that is the Fourier transform, you will do it yourself. Okay, once you see that lecture, then this is an exercise. Okay. Great. In classical case, this is called discrete Fourier transform, and thankfully this Fourier transform is a unitary matrix. This is not surprising. Fourier transform is a basis change matrix, so it should be unitary. And this matrix is actually very, very nice. So let's say we will keep n as to the power k. You have seen such matrices before. These are called van der Waals matrices. Right? The jkth entry is omega to the power jk, where omega is the nth root of unity. The exercises you will do is Okay, so these are all first two you can definitely do. These are linear algebra problems. This is a group theory problem. Okay, so these are the exercises. Obviously, if you are stuck, I am there. You will verify them. Okay, what are we going to do today? Clear? Once again, to re-emphasize the message, Fourier transform over z2 to the power z2 whole to the power k has been very helpful. So now we want to do Fourier transform over z to the power k. By the way, there are ways by which once we have done this Fourier transform, we will actually be able to do Fourier transform over any zn, even if this is not of the form 2 to the power k. But let's focus on 2 to the power k now, because we can write it as qubits. It's much simpler representation. Okay, but just after note, others can also be done with more work. Okay, so then our goal is to do this matrix f to the power k. We want to apply this on our state, on a quantum computer. We want to create a quantum circuit such that this unitary operator is applied. Right? What do we have? We have Hadamard, we have C0, we have 1 qubit gates, we have controlled 1 qubit gates. All those are there. Right? Using those, we want to execute this on a k qubit thing. Questions about what we want to achieve? This doesn't seem like a straightforward task, right? Okay, but that's what we want to do. And it's obvious, because first we tried the Fourier transform on this. That was very, very simple. What was the Fourier transform on this? Hadamard to the power k. That is easy. That we know how to do. Now we said we want to do Fourier transform over other groups. Other simple group is this. Simple, not in the group theory language simple. Simple means easy to understand group. Is this. Now you want to ask, this is the Fourier transform, can we apply it on a quantum computer? And it turns out in a certain way we can. What happens is, if you want to do it on classical computer, it takes this much time or these many gates. But there is a smart way to do it. It is called fast Fourier transform. It does it in n log n. What we are going to do is called QFT, which is much faster. Okay, I will say some. I think it is k square. We will check. Okay, but you see now, I have log now, right? K is log n. So we are really fast. But there is a caveat. Okay, so I'm not saying this is an exponential advantage, because QFT is doing a Fourier transform, but it is not really solving the DFT problem. So let me tell you what we are going to do, and then we will try to create the circuit. Let me write it the other way. Okay, so I want to apply this matrix. right? But since this is a Fourier transform, what it means is that x is coming from a function like this, right? So I have a vector like this. This gives me the function value at 1, at 2, at 0. Correct? So given these function values, I want to calculate its Fourier transform. Right? So that will be some vector like this. And how do I obtain this vector? I multiply f with this vector. Right? This f to the power k. Clear? This is what Fourier transform does. Classically, DFT, FFT, what will they do? You will give them x1, x2, x to the power k. It will give you explicitly what is y1, what is y2, what is y to the power k. Sorry. What does KFT do? Given state x, it will give you state y. Okay, so we will get this output not as explicit numbers y1, y2, y2 to the power k, but as a state. And you know, given a quantum state whose elements are y1, y2 to the power k, I can't really figure out the elements y1, y2, y2 to the power k. This we have seen so many times, right? So this is the difference. Even though it looks like an exponential advantage, but QFT gives me the answer only as a state whose coordinates are my Fourier transform. So I will need a state of x1, x2 to the power k. Even if you give me a state and do not tell me explicitly x1, x2 to the power k, I am fine. You give me the state, I will apply this matrix F and give you this as a state. It's a unitary matrix, so unit vector will remain unit vector. All that is fine. Sounds good? So you see the difference between what is doing classically. Classically, I will get each of these individually. You would know, I can ask you, what is yi? You will be able to give me yi. After quantum Fourier transform, that's not what we are doing. We have a state x, we apply this unitary, we will get the state y. We will have no clue what y1 is, or what y2 is, or what yi is. But still it is going to be beneficial. Where are we in the story? We wanted to do Fourier, and see, when we did Fourier transform over Z2 whole to the power k, it was the same thing. When we applied Hadamard on this, we will get the Fourier transform as a state, right? We will not get individual things here. So it's the same thing. We are, in the quantum case, we are saying how to apply this unitary matrix on the state vector. We are not saying we want individual entries y1, y2, y to the power k. Same thing we did for z to the power k. Now we want to do it for this group. And I have told you the unitary, so now it's a good problem for you. How should we do this? What is the quantum circuit corresponding to this unitary? Every quantum circuit corresponds to a unitary. Now I'm telling you a unitary, you have to construct a circuit. And it should only take order k square gates. How would you, suppose I had given you in quiz, I hadn't asked you here, how will you approach this? As a researcher, This looks like a giant matrix, right? Can you make it small?
We have to make it in like two-level matrices, products of two-level matrices.
In Lion, it's f of 4. That is 1i minus 1 minus I, so that is just a copy multiplied by.
Very good. So your strategy is probably looking at the matrix, but in general, when we are stuck in research, what do? We should try it for simple, small cases, right? And what is the simplest case? K equal to 1. For k equal to 1, what is F2? Don't look at this. What should be F2? Hadamard, right? F2 is a Fourier transform over Z2. So this has to be Hadamard. You can check. What is the second root of unity? -1. This doesn't give us any intuition. Let's move forward. Fine. I is the fourth root of unity. What do I get here? F4, that means omega is complex I, right? I'm just writing down that Vandermonde matrix. Now, this is different from H square. Why is it different from H square? Sorry? Yes, exactly. H only had what entries? Plus minus 1. Right? Now you have complex entries here. Is this Hermitian? So now you see the difference, right? Again, these two groups are different. And hence, the Fourier transform here is going to be much more involved. Okay? So let's try to make sure that we can apply this. Okay? And that will give us intuition of how to do it for k equal to 3 and k in general. This seems still okay, right? Remember, we can apply any, let's say, 1 qubit and 1 qubit control gates. If I can apply 2 qubit gates, then this is a 2 qubit gate. So let's just say you want to break it down in terms of 1 qubit gates.